So thank you everyone for joining today. I'm Shahriar Shanto, undergraduate student, third year at the Department of Electronics and Telecommunication Engineering at RUET. So the paper of interest today is this one, Deep Learning Improves Radio Frequency Interference Classification. But before we go to describe what they did, I will talk about the basics of radio astronomy or the importance of radio astronomy and what is radio frequency interference, then the main ideas of machine learning, deep learning, neural networks, convolutions, and then the work done in the paper and some other works and future directions in research. And this presentation also includes lots of photos of dish antennas. Okay, so radio astronomy is an integral part of observational astronomy, and up until now, it has won 2 Nobel Prizes in physics. The first one was for the discovery of cosmic microwave background radiation, which is regarded as direct evidence of Big Bang theory, and it was made through radio astronomy. So these 2 people were awarded the 1978 Nobel Prize in Physics for the discovery of CMB. And an interesting fact is that when you look at a detuned terrestrial television, about 1% of the signal you see is from the CMB, cosmic microwave background. So you are seeing the birth cry of the universe on your television. The second discovery was the discovery of first pulsars. Okay, so Belle Burnell was working with a dipole telescope, radio telescope in England, and she noticed a strange signal in her data. It was a data that was strong and repetitive. It had a consistent period. So initial fears were that it came from alien civilizations, but it was later realized that she detected a pulsar. So pulsar is actually a neutron star that is rotating on its axis, and 2 tight beams of radio waves are emanating from 2 directions. So on Earth, we only detect or observe the radio signal when the beams are directly comes directly towards Earth. Okay, so we detect it after a consistent period, like always. And this particular pulsar was located at the heart of the Crab Nebula. So this discovery was also awarded a Nobel Prize in Physics, but that actually went to her doctoral supervisors. And then, just this week, a discovery was made. So international group of scientists actually found signatures of phosphine at the higher clouds of planet Venus. So, and they concluded that the only way phosphine can be produced there is either our understanding of chemistry is lacking, has some lacking, or there is microbial life on Venus. Okay, so the chemists are really confident about what they know up to now. They said that phosphine can only be produced in a industrial setting or by a specific kinds of microbial life. So this is something to look forward to, and this makes a very strong case for a return mission to Venus, Project Venus. So we can understand that radio astronomy can be very useful, right? That's why we have many instruments, very large and useful instruments to listen to radio signals. The largest one being FAST. It means the 500-meter aperture, field aperture spherical telescope, which is the largest field aperture radio telescope in the world right now. It is in China. Then there's ALMA, LOFAR, JCMT, and this JCMT one was actually used to first detect phosphine in the clouds of planet Venus.
Maybe we can add here that to differentiate that FAST is a single dish telescope, so it is a single dish of 500 meters.
Single spherical telescope, yes.
And ALMA, LOFAR are interferometers, so they have hundreds and thousands of dish or station or antenna that are connected.
Yes.
Yeah, you can go on. Yes.
So their Arecibo, this was the previous the largest one.
So Arecibo was the largest, that was 300 meters.
Before FAST.
And FAST is, although you have to understand that FAST is very new, so people still don't know how successful FAST has been. So it's still very new and only in commission stage.
But the first light means the first received signal of a radio telescope. The first light of FAST was in 2016. So it has been quite some time now.
But still, it is pretty, I mean, in terms of groundbreaking science, it is still very new.
Yes.
Yeah, okay, go on.
So there's HERA, which is the hydrogen epoch of reionization array, which will be instrumental for detecting distinctive signature that will allow astronomers to understand formation and evolution of the very first luminous sources. So yeah.
I can add something that, you just saw the image of HERA on the Google map just beside Meerkat. And HERA, so HERA is actually coming up at the end of a long line of tradition of trying to detect 21 centimeter signal, again, coming from neutral hydrogen. And already there are 3 groups that were trying to detect this signal, one in the Netherlands, one in the USA, another one in Australia. But now the American group has this new telescope, which will probably have the first, let's say, useful detection. Well, it has been discovered already. But so the detection has been made already. You mean, of course, the 21 centimeter signal can be detected anywhere from our galaxy or nearby galaxies. That's very easy. And that was actually the first detection of radio signal was 21 centimeter. So even before CMD, hydrogen was detected in the 1950s. But of course, the 21 centimeter signal that we are talking about here, this is coming from a remote past, like 12 billion years ago. So that has not been done yet. Okay, you can go on now.
Oh, and then in 2021, the construction work for SKA, which is the Square Kilometer Array, will start. And its completion will usher in a new era of radio astronomy, because the SKA will be the largest scientific facility ever made by humans. Okay, we'll talk about that more later. As Asad sir was talking about HERA and SKA both will be trying to detect and make discoveries about the first stars and galaxies. And this was the time, I think it is called the cosmic dawn. And in this picture, the time is actually right about here, when the first stars came about, and HERA and SKA will try to detect and find evidences and do many other scientific research during what happened during this time, and many other scientific processes. And something about the 21 centimeter radio emission. The hydrogen atoms have 2 states, higher energy states and lower energy states. The higher energy state is when the proton and electron spins are aligned. So the spin is in the same direction. And the lower energy state would be when the spins are not aligned, anti-aligned. So when the hydrogen, the spin is reversed, as to say, the higher it goes from higher energy state to a lower energy state, it emits radio waves, and it is exactly 1420 megahertz. And again, if if the hydrogen atom receives a signal exactly the right amount or right energy and frequency, then it will go from lower energy state to a higher energy state. Okay, so this is the dishes in ALMA observatory, ALMA array, some more, and this is the very large array telescopes. And this is the Hera Asad sir was trying to show us. And then this is the largest one, FAST in China. The diameter is 500 meters. And seeing this picture, I have one question: that what happens when it rains on here? Something like any drainage system must be there, I guess. Okay, so the radio astronomy is actually interested in the frequency range of radio and microwave both. Okay, so, and coincidentally, or actually, that frequency range is also very useful. To us humans, we are using it for communications, right? Satellites, televisions, radios, and Wi-Fi and mobile cellular communications. So all those also use the same frequencies. And when we try to detect astronomical signals from far away, we are being interfered by these signals. So these signals are noise, actually, or radio frequency interference to astronomers. So radio telescopes are actually located far away, as far away as possible from human habitation, and still radio frequency interference is orders of magnitude stronger than astronomical signals. So we have to have some technique to carefully remove the radio frequency interference signals so that we can only see the signal or process the signal we are interested in, astronomical signals. And to
yes,
give an idea,
I was suggesting that we already spent 30 minutes on the introductory part, so maybe you should go into the RFI part more now. But you are already entering into that part now, right?
Yes, sir.
Yes. Okay. Yeah. Go on.
So the amount of data produced is very large, enormous. So like the SKA, the data produced by SKA would fill over a 5,500,000 GB laptops. That is the rate, the data rate of 5 terabits per second. And to process all this data, the SKA will have 2 supercomputers, and each of them will be 25% more powerful than current best supercomputer in the world. So there is no denying that we have so much data and also so much radio interference, radio frequency interference coming with them. So we have to have some robust technique to detect and mitigate the interferences from the data. Okay, so previously, many techniques have been used to flag and remove radio frequency interference from telescope data. The singular vector decomposition, principal component analysis, and then some threshold-based algorithms where the RFI is flagged when the signal exceeds some threshold in the 2D time frequency plane. Because as we said, the interference signals are actually many orders of magnitude stronger than the astronomical signals. So we first thought, or astronomers thought, we can use threshold-based algorithms to mark and remove the stronger signals, and then we can get the signals that we are interested in. So cumulative sum and sum threshold is like the standard of algorithm-based approaches. Okay, so then, and finally, researchers are also experimenting or researching with trying to use supervised machine learning to detect and mitigate RFI from telescope data, and especially deep learning, because deep learning can be used to to classify images very well, very efficient and very accurate. So here supervised means examples of correct answers were shown to the machine or the algorithm. Don't worry, I will try to talk a little bit more about machine learning and deep learning in general. So we are beginning intro to machine learning. First of all, what is programming? Programming is writing a program or a set of commands that the machine will sequentially exactly follow what the commands were and do whatever we want, right? So the logics are written by us humans. And what if I ask you to write a program to classify images that are of cats? Okay, so the classification of cat pictures. You cannot actually write a program to detect cats from every possible images that are of cats in the world. So we cannot do that with traditional programming. We have to use some kind of machine learning to solve this kind of problem. And in a machine learning approach, we show data to the algorithm. We show the questions we want answers to and the correct answers. Okay, so questions and correct answers. The machine learning algorithm tries to learn what is the pattern here, what is the relationship to questions and correct answers. Okay, then after seeing all the data sets, all the possible data we can possibly show it, it produces a model, a mathematical model, or any other type of architectural model that can then predict the correct answers. Okay, so one example I'd like to give today is many of us have, I think, wondered which house do I belong to if I got into Hogwarts School of Witchcraft and Wizardry. There are 4 possible choices here. So what we would have to do is show the machine learning algorithm a sets of questions and the correct answers for this problem. Okay, so we and by this picture I mean the characters' honesty, intelligence, and can he speak snake language. All right, so all the information about this character, all the data or features we can show to the machine learning algorithm, and the correct answer we want to get from the machine learning algorithm. Okay, so we do that for all possible sets of questions and answers we possibly can. Then after we have showed the machine learning algorithm all possible, as much as data we could, then the machine learning algorithm will produce a mathematical model. And this process of showing data to the machine learning algorithm is actually known as training the machine learning algorithm. And in this case, we can say the machine learning model or mathematical model that is produced is our own sorting hat. Okay, so then we can use the machine learning model or our sorting hat to ask our questions and get the answers, or to get the predictions. And this step is known as predicting stage. Okay, so there are different kinds of problems that we can solve with machine learning. The 2 major type of tasks in machine learning one is classification and another one is regression. So classification is when we are trying to classify data or inputs or questions to specific classes. So in our example, we had 4 classes that could the question or our input or our character could be in. So the machine learning model tries to learn the differences or the relationship between the classes so that we can ask our new questions, new data, so it can classify to any of the classes and with expectedly with good accuracy. And there's regression where we don't have any specific classes. We want a continuous value of something like price or luminosity uh, or probability, something like that. So in this example, we can say we are trying to predict the price of a house, and in this case, the input will be the features of the house, like how many bedrooms are there, how big is the house, what is the location, things like that. So this is regression problem. And now I want to tell you about the distinction between AI, machine learning, and deep learning, because we want to go here, because our paper of interest was using deep learning. So we have to understand what is the difference between machine learning, deep learning, and AI. So this Venn diagram actually shows the relationships between them. The AI is a big application-based field where they are trying to, people often try to make some system or a robot that can mimic human intelligence. Okay, so we can do that with machine learning or without machine learning. So that's why the AI has an area out of the area of machine learning. Okay, so AI can be done without machine learning, but there's a limit to what it can achieve. So most of the AI use machine learning, and then again, most of what is in machine learning that is very useful to us is deep learning. Deep learning means using neural networks, and we'll talk about what neural networks is. This is an example of neural networks where each of the circles denote a neuron, and neural networks are actually inspired from our human brains. And this actually approximates how the neurons in our brains are connected to each other. They are actually connected to possibly each and every one, and not all the connections are strong equally, right? We have some strong connections, then weak connections, and all those together represent some memory or some processing in our brain. And in the case of our neural networks, there's mathematics, right? So I want to focus on just one neuron. So one neuron is just a node, and it holds a value. And what is that value, or how is that value calculated, is this equation. And this is just an equation of a line, right? Equation of a line. So this is the input x, and this is W is the weight, and B is bias. So here we can see the input x goes through a connection that has a weight of W, and then it is added to the B, or bias. Bias is very specific to one neuron, and then what the output we get is Y, and this is the value that is held by this specific neuron. And there's something else to it. This is a function, obviously, and this sigma actually denotes a activation function. So as we know from biology, that our neurons in the brain are actually activated when they get a specific electrical signals, right? So activations are related very much. In our case, we also relate to that. We have an activation function that dictates how activated this neuron is, or how excited this neuron is. Okay, so this activation function are usually a sigmoid or ReLU or some other function, and all that those do is squash the values inputs to values between 0 and 1. And 0 and 1 is very extensively used in machine learning because 0 and 1 is like, as we know, in probability theory, the 0 means there is no probability, and 1 means 100% probability, or it's 100% certain that this will happen, or this is the correct answer. So we use that idea in machine learning also. So this is the function of sigmoid, and we can see in the graph that when the input is 0, the output is we get is 0.5, and when the input is larger and larger, the output goes nearer to 1, and it can be maximum 1, it cannot be greater than 1, and same as here in this negative side of the line. So this function actually squashes all the input values between 0 and 1. So this is the neuron and its equation, and the y value is the activation, which means how activated or excited I am by that input. Now, if we talk about an example, we know that images are like matrices of or tables of values, right? All those values represent each pixels in the image. So usually there are between 0 and 225, and so we have a table that we actually vectorize it. Image to vector means we vectorize the matrix. So it just means we convert it to a one long string of one long list of values, or a vector. That's more appropriate. And then we divide it with the highest possible value. This is called normalization, because we don't really want any values greater than 1. Like, we want the values to be between 0 and 1, maximum 1, minimum 0. So we do that, and these are the inputs to all the first layer of neurons. And then these neurons pass the value through these connections to the next neuron or next layer of neuron. And in this case, we have only one neuron here. We can actually have many more, and we, as we know from the equation, the input is multiplied with the weight of the connection, or we can say the weight is actually dictates how important is that exact value to you, to this neuron. So the value is multiplied with the importance, is then it is added to the bias of this specific neuron, and then the sigmoid function or activation function is applied. Then we get a specific value. This is the prediction of the machine learning or neural network, machine learning model or neural network. So what does this value mean? This is again because we used a sigmoid function. This value is between 0 and 1. So when it is 0.73, it means the neural network is 73% confident that the image that we gave it was a cat. So if it is actually greater than 0.5, it's a cat, we can say. Okay, so then actually I want to show you a real full-fledged neural network. So we have the input layers, then hidden layers. Hidden layers are just between input layer and output layer, hidden layers. And it is hidden layer because the values in the neurons we don't actually see. We actually input the values in the input layer, we get output from the output layer. We actually don't see the values in these layers in between. So they are called hidden layers. So let's focus on this specific neurons, because there is no calculation going on here. Just the input we give is passed on to this neuron. The actual calculation is done in the next layer of next neuron in the layer of next layer. So if we zoom into what this neuron is getting from the previous layer of neurons, is that the value is multiplied with all those weights. We can see here x11 is multiplied with w11, x12, this should be right here. There are many neurons, ... means there are more here. So x12 is multiplied with w12, or that specific weight from that neuron, and so on. So all those values are multiplied and then added, and then again added with the bias for this specific neuron is equals to the y1, or this output of this neuron. So we can see that this is actually a weighted sum of values from previous layer. Okay, so as we might remember from matrix multiplication, that actually the first row of the first matrix is multiplied with the first column of the second matrix, and the multiplication is exactly like a weighted sum. So 1 is multiplied with 7, 2 is multiplied with 9, and so on. So all that is exactly similar to the equation we saw of a neuron. So we can say that we can have a vector of the weights and the vector of the inputs. We can multiply them, matrix multiplication plus the bias is equals to y1. So this is exactly the same for
I think
all
you have
those
to
neurons.
speed up a little bit. Yeah, but
Okay,
go
sir.
on, but just speeding up a little bit.
Okay, sir.
Okay.
So we can finally see that all those calculations for all those neurons are reduced to matrix multiplications. These are matrices of the weights, matrix vector of the biases and the inputs, and then we get the values for first layer or one layer of neurons. So we do that for each and every, and don't forget the activation function that is applied to all the full value, all the value. So we get the values in first layer. So I will not go deeper than that, but I will finish it off with a simple example. We have photos of handwritten numbers. Okay, so it can be if the images are of 40 into 40 pixels, then we can say we have 1600 values. Okay, so we have to have 1600 neurons in the input layer, and then the hidden layers can have as much as neurons we want. Okay, and the output layers will have the number of neurons as equal to the classes, number of classes we want to classify to. Okay, so we want to detect in this example what is this number. So what is this digit? So there are 10 digits, so we can say we would have 10 output 10 output neurons in the output layer. So in this example, if we have a value of p5 equals to 0.8 and all the other p values are closer to 0, then we can say the neural network is actually predicting that this image that we fed into the network is actually a 5. Okay, it is correctly predicting what the character was handwritten. So I am only talking about predicting because the training stage involves much more mathematics, and I will just say that learning machine learning means finding the best weights and biases. Okay, so I talked about the weights in the connections and the biases in the neurons. So they all are just parameters that can be learned. So machine learning, when we do training, it is actually finding the best weights and biases. And the way they find the biases is actually using calculus, some basic calculus. They find the minima or maxima, depends on the application. So they find the best suited weights and biases that can predict the correct answers. Okay, so if you want to know more about how neural networks work, you can watch this series of videos made by 3 Blue 1 Brown He explains much better than me, and he uses animation, so you'll enjoy it. Then we talked about neural networks. Then what is convolutional neural networks? Convolutional neural networks
Yes,
are
I think
very...
this you should explain in 1 minute what is the convolutional part and then move on to the paper.
Okay, so
Yes.
convolutional neural networks have some layers that do convolution. So what is this convolution thing? Convolutions is like just photo filters like we use in Instagram. So, and also the convolutional neural networks have pooling layers. Pooling layers is just compressing the image or subsampling the images. For example, if you have 12 megapixel image, then it will be converted to a 6 megapixel image. It is halving the number of pixels in an image. Okay, so this is an example. We can see what happens when we do convolution and pooling to an image. So this is a data set of fashion items like shirts, t-shirts, and sweaters. So if we do convolution, we can see that convolution actually amplifies the important features of the image. So this helps the machine learning algorithm to learn and differentiate between all other items. Okay, so and in practice, the convolution layers are done in numbers of more than one. Okay, so in this example, there are 4 layers of convolution sampling. Okay, so some examples I wanted to show you. So this is for pictures of horses. So we can see that the actual features of a horse, the shape of a horse, is amplified by doing convolutions. This is how
I think there
convolutions.
is also a question from Arshad sir. Can you see in the text?
Okay, so I have to.
Okay, it is actually what would this reflect? I can tell you what would this
Okay,
reflect in the weight matrix. I
what
think
would this reflect? What would reflect, sir?
I think the convolution part. Is it
Convolution part? So if we see here that convolution layers are the first layers in a simple convolutional neural networks. So convolution layers and pooling layers actually simplify the image to be learned by the neural network. Okay, here. So the weights and biases in the neural network layer is they only need to learn the simplified version of the image we fed in the simplified version or amplified version. They are the convolution layers are actually extracting features from that images and then feeding to the neural network. So the weights and biases only have to do a little work of understanding what those simple features or images are. If we were not to use some if we didn't use convolutional layers or pooling layers, then the whole image is very noisy and it contains very too much of information because it has color, it has texture, which is not always so helpful to classify an image to understand this is a cat. So all those colors, patterns is not really important in most cases. So we simplify the images using convolution layers and pooling layers. So this speeds up the learning process, learning time, training time of a machine learning. So we are finally getting into the paper. So I can expect you to understand what is deep learning, what is radio frequency interference, and what is classification. So now we actually understand what the title means. This is the first step of understanding a paper. Okay, so what the paper actually did, same as any machine learning work, is collecting some data from some sources, building a model, training a model, and comparing the results.
Arshad said that you did not explain what is deep learning. Well, you said that deep learning is whatever uses convolution, whatever uses neural network, right?
Yes. So yes. Deep learning is actually just machine learning done by neural networks using neural. And why is that called deep learning? Because we have some layers upon layers of neural networks that is deep, normally much more deep than vanilla machine learning, as it's called. Vanilla machine learning doesn't have deep equations or long matrices of calculations. It doesn't have that. It just has some architecture, some simple architecture, or some simple algorithm, or just an equation that is that is fitted to the data. Okay, like linear regression, polynomial regression, that is vanilla machine learning. That is not deep learning. So deep learning is done using neural networks that has layers upon layers. So that's why it is called deep learning. I think that answers his question. So as I was saying, that the data sources, they collect some data sources, then build a model, train the model, and compares the results. So they used the first data source for them was the hide and seek package. So hide is actually H1 data emulator, and seek is signal extraction and emission cartographer. And this package of software was actually made in ETH Zurich, where Albert Einstein once studied and lectured. Okay, so data source 1 is hide and seek, 2 independent software packages that simulate and analyze single dish. This is a keyword, single dish radio survey data. Hide can produce survey data, add some noise or RFI, and seek can process simulated or real observed survey data, and it can remove RFI using some threshold. Again, we talked about this. This is a threshold-based algorithm to detect RFI and mitigate it. So they used 13 months. They actually simulated 13 months of survey data using hide and seek. Okay, data source 2 for them was a simulator for interferometers. It was not available at the time, so they created one. It simulates the Meerkat telescope array. So Meerkat simulations include a simplified primary beam model that was fitted to a Zernike polynomial representation. They got it from a paper of our Asad sir. So they used the model, beam model from his paper, and created a simulator. So they produced total data of 1.5 terabytes for this particular data source 2. Okay, then data source 3 for them was real data from Karoo Array telescope, or CAT7 telescope, which was then human leveled, or a team of experts actually marked those RFI signals and produced masks. Masks means just a picture of where the RFI is and where it is not. Okay, so they actually used this data source 3 as ground truth, which means the correct answers to feed the machine learning model. They regarded this as the ground truth. Okay, so what is the task? Task is RFI flagging and mitigation to remove all the signals or pixels because the data from telescopes are actually represented in time and frequency 2D plane, so it is much like a image. So all those we want to remove all the pixels, or mark all the pixels that are contaminated by RFI. So we can say that those pixels will need to be marked as either RFI or non-RFI, or we can say 2 categories or 2 classes, which means this is a classification type of task in machine learning. Okay, using machine learning. Okay, what is the model they used? They built a model called RNet, and UNet is a previously known good example of a machine learning deep learning model to mitigate RFI. So they are just comparing the models, their model and the previous model. So RNet is just as the picture depicts, it has convolutional layers. We can see here convolutional layers. Yellows are convolutional layers. These gray are ReLU. I talked about it is an activation function, and an important feature of their model was a skip jump, which means a highway or a bypass highway for the values in the picture. So skip jump means that in the initial stages of the machine learning, their training, machine learning training, is done by using by switching on this bypass. So the values directly go to this third layer. Okay, so the first two layers are not trained. The weights and biases in the first two layers are not learned initially. Okay, so they train for some time, the later layers are trained, then at finally they turn off the bypass, then the data flows through the first layers, and this really speeds up the training process, and they really get a good accuracy from the model. Okay, so this is the data, actual data collected from telescopes, and this is the ground truth, which means the human labeled RFI mask, and this is the
maybe mention again that here you have this is the time frequency data.
Yes, yeah, the signals are actually represented in time by frequency domains. Time in this domain and frequency in the y-axis. Okay, so our RNet prediction is this one, UNet prediction is this one, and SDB flagger is a default flagger in another machine learning. Telescope array. I think it is a built-in RFI flagger for Meerkat. Okay, so we can see that this has much more yellow pixels than the ground truth, which means this SDV flagger marked those pixels that are not really a radio frequency interference. So we can say it has much more false positives than the other ones that we see. The RNet is really close to the ground truth. The UNet has some false positives, but the SDP flagger, the built-in flagger in Meerkat, is actually having much more false positives. So we can say the RNet is fairly more accurate than other works. The UNet was the previous very good machine learning model, so it surpasses the previous best model. Okay.
Actually, there are two questions related to this. Maybe I can tell you. One question is, UNet is mostly used for segmentation purpose.
Yes.
Is RNet something like that? If yes, then was it used for something similar to segmentation here?
Yes, it is true. So both models are actually used in image segmentation. The UNet was first used in biomedical imaging, so like detect cancer or other disease.
Maybe also say for the others who don't know what is segmentation.
Segmentation exactly means classifying the images, or yeah, that's exactly what it is. Classifying images into classes. Like we can have a X-ray scan of a perfectly healthy human being and someone who has pneumonia or a cancer in his body. So we want to use machine learning that can do image segmentation or classification to correctly classify the images, so we can detect which one is the healthy one and which one has the cancer or has the disease. Okay, that's yes. What image segmentation is. So UNet was very well known for image segmentation. Then the astronomer was very smart enough to use that architecture and adapt it for this application. Then RNet, again, this is the ResNet. ResNet is very known, very much known as a image segmentation for image classifying images. And then again, this researcher also was inspired from that and built a model according to it and got very good results. Okay.
Another question is, what loss functions do the models use?
Okay, so loss functions are of very wide ranges, like mean square error or absolute mean error or RMS
I think he meant in the paper, like in the paper, what loss functions do they use?
In the paper, they used MSE, mean square error.
Oh, okay.
So this lists the values of F1 scores. F1 scores is just a very good parameter to show it is if it has good balance of precision and recall, and so we can see that RNet is actually the best one in terms of F1 score in all those data sources: height data sources, Meerkat data sources, Cat7 data sources. Okay, so Cat7 one is the real observation that was hand leveled, and it got 85% accuracy or 85% F1 score for that particular data set. Okay, so for the height simulations, this is TPR, which is true. This is true positive rate. This is false positive rate. Okay, so we want to minimize false positive rate and maximize true positive rate. Okay, so this is the plot. The red and blue one, we can almost, I can barely see. We can barely see that the red and blue one is for the RNet, and the yellow and green one is for UNet, previous best known best machine learning model. So RNet actually surpasses the previous one. And here we have plot for precision and recall. And precision is actually means that of all those I classified as true is actually how many of them are actually true. Like I said this person has cancer, and in reality how many of them actually had cancer. So how precise my predictions were. And recall is how much of the true possible cases I could classify, I could detect. So it means if a machine learning model says that this person has cancer, but missed out some of the cancerous images, but so that is the parameter of recall. If I can classify correctly or collect all the possible instances of cancer, so that no possible true values are missed out by me. Okay, so we also want a balance between them, because there is no possible way of having both very good. We can just barely have a balance between them. So this is the contour here in the image. Contours denote ISO F1 score. So we can see that same F1 score can be of a low recall, higher recall, low precision. Then again, the same F1 score can mean higher precision but low recall. So we can see that for the case of RNet, the precision and recall both were very much in a good range, and it surpasses the previous model. Same is true for Meerkat simulations, and again for Cat7 simulations, the same thing: true positive rate, false positive rate, the recall and precision balance. And we can see that, and there's another story here. The researchers were very clever to use this. It is known as transfer learning, and in transfer learning we actually use the previously trained model, and then we train it for another data set. So as we said, we had 3 data sets: Hyde, Meerkat, and Cat7. So they first trained with Hyde and Meerkat. These are the simulated data sets, and this is the real one. So they knew that the simulated data sets are the real observatory data sets are different, because the real data set has some complex noises or realistic noises, and very much more complicated radio frequency interferences than the simulators, because the simulators only can simulate so much. It can only simulate the equations we give it or the logics we give it. So this will be much harder or different than the actual
also
simulated
mainly
data set. So
also mainly because all the sources of RFI might not be known, and also
might not be known. Yes.
Also, the problem is the sources are time varying. So we are assuming that, okay, at like during the night, for example, aeroplanes are less.
Yeah.
You have less aeroplanes, but satellites, same number of satellites. So sources would vary, but it would be extremely hard to exactly simulate.
Yes, exactly. So we can say in one sentence that the data in the Cat7 Cat7 data set will have more uncertainty to it, right? So the machine learning model will suffer to understand it or learn from it. So they use transfer learning. So what is this means is we turn off the weights and biases in the first 3 layers. Okay, so why we do this is so that we don't lose all that we have learned from previous databases. Because when we train with simulated databases and then again without machine learning we train with Cat7 databases, these weights and biases will try to adapt to the real observations, right? So these weights and biases will lose what they learned from previous experience or previous exposure to the database data. So we freeze the weights and biases. We only train the later layers with the Cat7 data. Okay, so this improves the accuracy for the Cat7 data or real observatory data to in many much orders. So we can see here that without the dotted lines or without transfer learning and the continuous lines are of the using transfer learning or transferred RNet. Okay, so we can see the transfer learning had a really big impact to the precision and recall here, and also the true positive rate and the false positive rate. Okay. So this actually concludes the paper. This was all that they done, but I wanted to show 2 more papers. Actually, I will not discuss them. I'll just show the architecture.
Yes, because we have 2 more minutes.
Yeah, yes. Okay, sir.
Okay.
So this is another one architecture. This is exactly looks like a U. So it is actually inspired from UNet. If you see the architecture here, this is called UNet because it is shaped like an U, because the shape of the data is decreasing first and then increasing again. Okay, so I'll not go into the details here, but it is shaped as a U, so it's known as a UNet. So they used similar technique and they gained a very good score, F1 score for FAST, the big spherical single dish telescope data. And this was actually observation, means the real observation data. So their RFI net, what they call their RFI net, actually got a very good F1 score for fast real observation. Again, this is not informatory data, single digit data, but it's a good job they did. And then again, this paper, they didn't use any kind of machine learning. They just use signal processing and things like that and algorithms. So they could very good accuracy, they could reduce the amount of RFI data and also fast radio bursts from the data. So these researchers actually help to produce better machine learning algorithms, because machine learning algorithms usually depend on the data. The accuracy of the data means the much more accuracy in the machine learning algorithm. I mean, machine learning cannot surpass the data we feed it. Okay, so I think this is a good sentence to finish it here. And future research areas can be reinforcement learning, temporal convolutional networks, and BASNet. This is another network, some more networks. They were researched recently in 2019 and 2020. So these are used in object detection. So I think we can leverage the ideas of it, and you can see in the name, it is U square net. So it means it is inspired from UNet. Okay, so it is used in object detection. I think we can also leverage it to in the application of RFI mitigation. So reinforcement learning is a big area of research right now. The AlphaGo, the machine learning agent of uh, a machine learning player of the game Go, which actually won against the best player of Go in the world, and it is also used in autonomous vehicles like in Tesla Auto Drive, uh, self-driving systems, so and much more. Okay, so robots can learn to operate, to move themselves, all the notions of locomotion just using reinforcement learning, very much comparable to human programming. Okay, so robots nowadays really do not need
So I
human
think
programming to do a
so. I
good.
think you should end on
Okay,
like what you think would be the best option for doing further things in RFI detect. Do you think
reinforcement learning can be a big one, because reinforcement learning really doesn't depend on data. Reinforcement learning produces its own data. Like, reinforcement learning means the machine learning model plays with itself. Like, it plays by the rules. We give it the rules. It's like playing a game. So when the machine learning algorithm does something good, it gets a point. So it thinks that whatever I did was really good, so I should keep doing that. So it goes on playing and learning what steps and what logics are really useful for this problem, then becomes better and better in that game, and that game can be any application. So I think in this
Oh,
particular RFI mitigation also, reinforcement learning can be useful.
mm. Okay, I think
So this is the end, I think. Thank you, and if anyone has any questions.
thanks a lot. I think that was really useful because I think although it went a bit too long, but that was good that you also went through all the basics so that we could connect
So
everything with
everyone can
everything else.
understand. Yes, thank you so much.
Yes, also for me, of course, I don't understand quite a bit still. So what I was, Arshad sir also said how would this help us to understand the astronomical data. So of course, that is the key part. I actually wanted to show a picture of how RFI actually affects real observations. So one, I don't know if, well, if you still have 2 minutes, maybe I can show it still. Uh, just to end on a bit more astronomical application. Uh, I will basically open the paper that I'm writing now. Well, it is finished, but what Shanto is doing, and we might do with Shanto as well, might be relevant for what we are doing, for example, here. So in this paper that is at the last stages of publication, this is Meerkat. So as Shanto was saying, they used only Meerkat simulated data, right?
Yes, sir.
They had
Meerkat and height
Cat7.
simulated data, and
Yes, they
Cat7
had
was the real observation.
Yes, so for Cat7 was a previous version of Meerkat. And for Cat7, they took
Yes.
real observation because they had commissioning data. There is something called commissioning data. Now, if I go to this paper and, for example, check something called, okay, I'll just show you this image. So this is actually a real observation, although it is not an observation of a specific object. This observation was done, well, the observation was of a galaxy, let's say. The galaxy was at the very center, but then the galaxy was removed. So when you remove the galaxy, what you get is actually the response of the telescope. So this is the response of the telescope that we calculated, of this telescope, Meerkat. Of course, the observation was done by the Meerkat people. Then we made a model of the observation. Now, of course, this is at a single frequency. If you so the response of the telescope, right? So this is the center of the field of view of the telescope. And if you go that way or that way, I forgot how much you can go. 1, 2, 3, 4, oh, 10 degrees. So it is 10 degrees in diameter. See, so 5 degrees on this side, 5 degrees on that side. So it is showing you 10-degree field of view of the telescope, of this Meerkat telescope. Now, this is at a single frequency. It is at 170 megahertz, written in the caption. But now if I go to, now we made a model of this, but we wanted to make a model like this for all channels. But we cannot do that even, because if you don't have a model like this, you cannot do any observation, because in real observation, your actual data will be convoluted with this direction sensitivity, the field of view of the telescope. So if you cannot correct for that, literally any observation that you do is useless. And not any, like if you're observing a very small point source, and if the point source is at the very center of your field of view, then probably you would be fine. But now, if I want to do broadband and large field observation, so if I want to see everything within 3 degrees, and if I want to also see that 3 degrees at all frequencies, then I need a model like this for all frequencies. But the problem is, even the model like this cannot be made for all frequencies because of RFI. So for example, if I go to the frequency part where we're doing the frequency modeling, of course, the modeling part is here very childish. So I'm not concentrating on that, but actual observation is very difficult. So anyways, so if you go here, you will see that, okay, it's not that clear actually here. I have to probably show, because I wanted to get rid of this frequency. Okay. But you can still see. So for example, if you check this curve here, this is the frequency behavior of those models, going from 900 to 1600, let's say 1 gigahertz to 2 gigahertz. Now you'll see that in many places, the data is really bad. So basically the places where you don't have data because of RFI. So there are at least 3-4 different patches within this frequency band. One patch would be around 11 to 1200. Another patch would be from 900 to 1000. Another patch there. So for example, here you can see a lot of scatter. So those places, there are like 3-4 bands within this frequency. That will be affected using this mechanism. So then Arshad sir asked about deconvolution. Well, I think now it would be too difficult to explain it. But of course, here we are not doing any deconvolution. Because in the primary beam case, of course, yes, to finally correct the data completely, you have to do a deconvolution. Normally, well, you can do 2 things. Although, like the simplest childish thing to do would be, well, that is done for most of the observation. That might be enough. If the point source is at the very center, I can take the image and just divide that by the primary beam. Then all the values are corrected on. But that can only happen if I want to just do a single observation at a certain channel. But in reality, we actually have to do deconvolution. And that deconvolution is done in something called a Fourier space, which would be too difficult, I think, to go now. And also, we don't have time. But anyways, does anyone have any comment? And Shanto, so thanks again, Shanto. I think, so I just wanted to finish with this thing that RFI would be very important. And I think we now have some idea of what can be done. Of course, many things has been done, but we can also collaborate with people in South Africa and also see what can be done in terms of using things that computer science or electrical or in general engineering students are learning from here.
Thank you, sir. Thank you, Arshad sir, and everyone.